Good morning, my dear students. Today I'll be starting with Environmental Engineering 2. So, before the beginning of the class, let me give you a little bit brief description, the brief syllabus or what I'm going to teach for this whole semester. So to begin with, Environmental Engineering 1, we have already discussed different mechanisms, different parameters, all the basic fundamentals of Engineering 1, environment. Now in Environmental Engineering 2, maximum it's going to be based on the designs of all the units. So before starting, let me give a little bit of basic concept. Main part will be design. So design means what? The design means in Environmental Engineering 2, the design means the design of all the water treatment plants and wastewater treatment plant, or maybe industrial effluent treatment plant. We also call effluent treatment plant units. So maximum students during the preparation of the GATE exams or engineering service or any public service commission, students got confused with what mechanism and what methodology to be adopted for designs. So before beginning the main topic, let me give the little fundamentals of design, so that you know that why I'm trying to solve this problem, why I'm doing this. Firstly, design means nothing. It is the calculation of the volume plus the dimensions. Number one, if it's circular tank, then it may be diameter plus the depth. If it is the rectangular or circular, it is the length into breadth into depth. Our main motive is to evaluate what is the diameter and depth, what is the length to breadth to depth. In Environmental Engineering 2, we have different type of tanks. Like say for example, you have the grid chamber, you have the primary sedimentation tank, you have the secondary sedimentation tank, you have the flocculation tank, then you have the chlorination tank, then you have your biological treatment units, like as per your syllabus, ethical stress process, tripping filter, and sometimes the UASP, the anaerobic part. So, in any question comes in the GATE exams, you may forget a formula, you may forget the mechanisms, but if you know this basic concept, you will be able to approach at least so that you can get 40 to 60% of the marks, because we give the marks based on the steps of a design. Okay. Now, design means what we are going to design. I told you volume. There are two formula we are using. Number one is simple thing. Volume is equal to Q into T, whereas Q is the discharge and time is, we call it hydraulic retention time or any contact period or detention time. Fine. So discharge will be given. If you know the HRT, you can find the volume. Number one. Another aspect is, you know that the continuity equation Q is equal to area into velocity. So area is the one we are going to design. If you know the velocity, then you can find area. That is, velocity is equal to Q by A. So my point is, you won't find much in the textbook or in other maybe theoretical teachings. From my experience, what I learned is there is two approaches to go for any design in environmental engineering. Number one is you have to find out what is the HRT. If you know the HRT, into the charts, you can get a volume. So, what is the HRT of grid chamber? What should be the HRT of PAST? What is the HRT of SST? All these things, we want marked up. We have to remember, we want marked up, but I'll tell you the basic concept. Number one. Number two, if you know the velocity of what? In engineering, environmental, velocity means at what velocity the particle settles down in grid chamber, at what velocity the particle settles down in primary sedimentation, secondary sedimentation, and flocculation. So if you know the velocity, then you can design the volume and the dimensions. As simple as that, I will come to the conclusion for these fundamentals that there are two basic operational parameters. I will say operational parameters, operational, or I will say design parameters, design parameter. Please remember, this thing you won't find in the textbook. Number one is the Histart or hydrogen time or detention time. Number two is settling velocity. The ultimate objective of this syllabus is we have to know how to find HRT or the settling velocity for different type of tank. So now, coming back to the main topic again, I am going to discuss first how this settling velocity will be determined. Because if velocity is determined, Q will be given, therefore area you can find out. And that you can assume based on the textbook, like maybe 2.5 meter to 3 meter. That I'll come later. So, to begin with, let me go with how to define settling velocity and how to estimate. I'll give you 2 seconds. Fine. Okay. Now, the first topic is, we call it sedimentation. When a particle settles down in a liquid, we call it sedimentation, as simple as that. When a particle settles inside the water, it may be in different forms. Say, for example, when you throw a piece of stone into the liquid, it will settle very easy. But when you see that sometimes in your village, if you put some coagulant in a muddy water, the settlement of the muddy water becomes very slow. That is also sedimentation. But the sedimentation is different. One is very fast, one is very slow. In another way, I'll give you another example of sedimentation. During the 2nd October or the Irabot Day in Manipur, the clubs, the locality, they used to clean the streets, the drains. For drains, they used to clean all the mud, right? And they used to put on the side of the drains. And you'll see the heap of the mud near the drains. But after 2-3 days, you'll find that the mud decreases the volume like anything and it becomes dry. That is nothing. The particles in the sludge, they are also settling down. As simple as that. Due to the gravity, the particles comes down. That is called sedimentation. But the concept is different in terms of particles settling in the water, like sand particles, or particle like flocks, or particle like in the sludge that settled near the periphery of the drains. So all these are sedimentation. To make the design easy, we classify sedimentation as type 1. Second is type 2. We have type 3 and type 4. These two parts is not much in the syllabus of BTech, only the theoretical part is there. I'll emphasize later words. For type 1 settling, I'm going to be here. This is the main important one. Now, this is a beaker. particle is settling down. Okay. Now, first point is the particle diameter is in range of 0.02 to around 0.2 mm. This may vary in different textbooks. It's not very important. Number two, the specific gravity of the particle is greater than 2.65. From these 2 points, what we draw the conclusion is the particle is heavier than the water by 2.65 times. The best example is cell particles, grid particles. During the solid mechanics, when you do SIF analysis for a cell, you know that the specific gravity of the cell is 2.65. That means the type of particles settling down is like grain particles. But what about the size? The reason is, if you take a piece of paper, you crumble it, or simple, you take a thermocol and make it settle down. Thermocol will not settle down in the water, even though the size is bigger than this, because the specific gravity of the thermocol is very, very light. That's why. So, these two combinations is very important, that a particle of this much size with specific gravity, and this type of particles are always grid in nature. Number three, when this type of particle settles down, another condition is there. You may have seen that a mud particles, soil particle, you make a ball and you make it settle down. It crumbles and it's scattered. We don't want that. This classification is especially for the particle who doesn't change, or I'll say alter, shape and size during settlement. Okay. And a particle having this type of properties, when they settle down, what happens is they settle with a constant velocity. Such particle possessing all these properties, we call it discrete particles. So, firstly, this type of settlement happens in grid chamber, especially. Example is grid chamber. Now coming back, we are going to design the grid chamber. And I told you before, designing the grid chamber means nothing. You have to find a settling velocity of this particle or the hydraulic retention time. Hydraulic retention time, I'll explain afterwards. But let me explain how to find the settling velocity of these particles. So that by knowing the velocity, we can design the area. And this type of settling is called type 1 settling, or we call discrete settling. Sometimes in 2 marks, match the following, we get exams, they ask type 1, different names. The answer is type 1 is discrete settling. This is important, you have to know. Okay? Now, let me do the derivation of how to find the discrete particle settling. This derivation itself, it comes in Manipur Public Service Commission for 30 marks, sometimes in the GATE exams or engineering surveys. The derivation itself is very important. So what I'm going to do is, I simply am not going to derive, but I'll derive in such a way that it will be very, very difficult for you to forget. You know the basic concept, you can derive very easy. Okay. So let me start from this side. Okay. Now, first, when this particle settles down, let me see, there is one force acting that is called, number one is the force of gravity. Any particles that will settle down due to the force of gravity, we call it Fg. Therefore, Fg is equal to simple mass into acceleration. But here, it is not very easy for us to find the mass of every particle. To make the things easy, how we convert is this mass can I write like this: density of the particles into volume of the particle into acceleration due to gravity can be g. This is equation number 1, force of gravity. So density into volume of the particle. You may say, so how can I find the volume of the particles? That's another question. But since it's very, very, very small, we'll assume that this particle is spherical in nature. So for spherical particles, we know that the volume is 4 by 3 pi r cube. So the diameter, already we have lump sum from here. So we find a volume, density is there. So G is acceleration due to gravity. Now here, it is coming down with Fg. The moment the particle settles down, there is a new force that is coming up. That is called, number 2 is force of buoyancy. It's called Fb. So Fb is also nothing. It is equal relation. Then the density of the water into volume. Volume will be same volume. So I can write volume P or volume into the acceleration due to gravity. Fine. This force is the upward force. So this is downward force, this is upward force. So another force is coming up, there is Fb. What happened is, if the density of the particle is more than the density of the water, the particle will settle down. If the density of the particle is lighter than the water, then it will flow. Example is ice. Ice density is lighter than the density of the water, so definitely specific gravity is less than 1 for ice. That's why it floats. So these two nullify the force, and F net is equal to 1 minus 2 implies to F G minus F buoyant is equal to density of the particle into volume G minus density of water volume P into G. So I can write as density of the particle minus density of the water into volume into G. This is equation number 3. This is the F net. Now, the moment the particle settles down, it is going to settle down with this force. Fine. Now, the next part is, remember, whenever a particle settles down with an F net force, or the difference between the gravity and the buoyant inside of water, there becomes a new force that introduces a new force that was never there before. But due to this force, it develops. That force is called drag force. Say, for example, you are trying to put a pile inside the soil. Inside the soil, there are no force. But the moment you put a pile, there is a frictional force that lies on the surface of the pile in the soil. Frictional force. So that is called drag force. The drag force evolves or introduced due to the moment of the F net inside the particle. So this drag force from physics in class 11 12, you know the drag force I was equal to. It is always proportional to find the area of the particle. Area means the cross-sectional area of the particle when it comes down. Then velocity, certain velocity squared by 2 and the density of the water. If the density of the liquid is very high, it will affect. If it's glycerin having high viscosity, so that friction will change. So this also plays a part. Fine. And to make the things equal, we put another coefficient called drag coefficient. So CD is the drag coefficient. Okay. So now what happened is, this is equation number 4. This net force is going to be equal to the F net is going to equal to force of drag. Therefore, rho P minus rho W into volume of the particle into G is equal to CD, area of the particle, into velocity squared divided by 2 to rho W. Now, we assume that the particle is spherical, even though it may not be exactly spherical. So what happens is, in some textbook, they provide a correction factor, okay? They provide a correction factor called phi, but we're not going to use it. If it's equal to 1, that means it's exactly correct. If it's equal to 0.9, 0.8 means we are considering the shape to be completely spherical 90% or 80%. Here we are using 1 for easy calculation. Therefore, from this equation you can see what happened is, we want to find out the velocity. Therefore, velocity squared is equal to rho P minus rho W into volume of the particle into gravity into this 2, I'm bringing it here, divided by CD into this density of the water into area of the particles. From this equation, this volume of the particle to area of the particle, let me see. Volume of the particle by area of the particle, this is 4 by 3 pi r cube. Area of the particle is, since it is the top view, we consider this one to be pi r square. So if you cut it, r square in r3, pi in pi, we got it 4 by 3 r. So 4 by 3 r is equal to 4 by 3 d. D is diameter by 2. So this we got, if you can say 2 by 3 of d. Okay, so this volume P by AB is equal to 2 by 3 of d. I've got this part, okay? Now, this equation, velocity squared is equal to rho P minus rho W by rho W, rho P minus rho W by rho W into CD, then 2 by 3 of D, 2 by 3 of diameter into G into 2 is equal to 4 by 3 G D rho P minus rho W by rho W into C. In other way, what we can say is, this also can be said is 4 by 3 GD by CD rho P by rho W. This will be density of the particle by density of the water. This will be specific gravity of the particle minus rho W by rho W. So this equation is called equation of terminal velocity. This is, so I'll say velocity is equal to nothing to the square. I think it's very clear. So this is the terminal velocity equation. Or else you can write this equation or this equation. If specific gravity is not given, we can use this equation also. So final velocity is equal to 4 by 3 g by cd d specific gravity minus 1 whole root over. And mind you, this equation itself sometimes asks in 2 marks questions. You should know the derivation as well as, in other words, you should even have a mug up in your mind. You should practice so much that you should be able to remember this equation itself. Okay. Now, CD. CD is a drag coefficient. What we have, the thing is, we have different types of flow. Different type of flow like laminar flow, transitional flow, turbulent flow. In this equation, we have not derived what is the type of the flow. Based on the type of the flow, the value of the CD will be changed. Okay. Now we'll see. Number 1, 4, laminar flow. How will we define laminar flow? Laminar flow is the flow where Reynolds number is less than 1. Here, CD is equal to 24 by RE. Okay? Number 2, if it is a transitional flow, Reynolds number is in the range of 1 to 2000, and CD is equal to 24 by RE plus 3 by root over RE plus 0.34. Number 3 is, if it is a turbulent flow, then CD is equal to 0.43. That means RE more than 2000. Okay. Now we don't know that the flow is either laminar or transitional flow or turbulent flow. Now you may ask again in between, what is Reynolds number? It is all your basic fundamentals. Reynolds number can be defined as what? Velocity into diameter, right? By A. Okay.